Hi guys, back again. This time we're going to learn about power and how that works. So recently we've done the conservation of energy and the unreasonable effectiveness of mathematics, and now we're going to learn power and also light bulbs. Very useful to learn. So let's get started with that. So think back, if you're doing the conservation of energy problems, you're supposed to look at your sketches, and for each sketch, you ask yourself these three questions. What is the question for kinetic energy? The question for kinetic energy is it moving? Because if it's moving, that means if velocity does not equal zero, kinetic energy won't be zero. What is your question for gravitational potential energy? You should be asking yourself, is it at a height greater than zero? Because if it is, then there will be GPE. And finally, the question for elastic potential energy, is there a spring that is compressed or extended? So hopefully you remember those. Those are very useful when you're doing. Those are very useful when you're doing the big conservation of energy problems with the whole strategy and all the steps and everything. So you all complain all the time about how difficult it is to get from the lower level up to the third floor. Yeah, you've got a reason to complain. Gravity makes it difficult. So let's think of this and try to remember. Think of this in terms of things we've already learned so far this year. Good review of those things. So if the combined mass of you and your books is 67.5 kilograms, with what force does gravity pull on you and in what direction? So think back, what is your formula for the force due to gravity? That is F sub g is equal to mg. So you plug in for the mass, you plug in for g, and you get that force. And what direction is it? Well, it's going down. That's gravity. It likes to go down towards the center of the earth. So if you were to walk up the stairs at a constant speed, how much force do you need to exert in what direction? So the operative words here are at a constant speed. So if you're not changing speed, that means you're not accelerating. So if you're not accelerating, well, think of that in terms of what is the most important thing you've learned in physics all year. That's F equals ma. If a equals zero, that means F equals zero. So not the individual forces equal zero, but the sum of the forces equals zero. So if gravity is pulling down on you with 661.5 newtons, you must be exerting 661.5 newtons up. That way the net force on you will be zero, and you can move up at a constant speed. So if you go up the stairs and you're exerting this much force, and you're going a vertical distance of 25 meters, how much work do you do? So think back to your formula for work. That is, work is equal to FD cosine theta. So you plug in for F, for D, and cosine theta. So what is the angle between these forces and the displacement? Well, your displacement was up, and the force you're exerting is also up. Therefore, the angle between them is zero. So cosine of 0 degrees gives you 1. So this number times 1 gives you 16,537.5 joules, which sounds like a lot, but joules are fairly small amounts of energy. So yeah, that's a reasonable number for this. So if you wanted to walk up the stairs and your vertical velocity was 0.625 meters per second, how long would it take you? And how about if you ran up the stairs with twice that velocity? So what formula relates velocity, distance, and time? The formula is your basic definition of velocity. Velocity is distance over time. So solve that for time, and you get t equals d over v, distance over velocity. So you plug in the distance and your walking velocity, you get 40 seconds. If you plug in your distance and your running velocity, you get 20 seconds. Well, if you're running up twice as fast as you walk, it should take half the time. So that's where that works. So do you do more work if you walk at that speed or if you run at that speed? So think about that for a second. And the answer is it's a tie. You don't do more work in either case. Velocity doesn't appear in your formula for work. Magnitude of F times magnitude of D times the cosine of theta. Velocity is not in there. You're doing the same amount of work in either case. So what's different? It's obviously harder to run up the stairs than it is to walk up the stairs. The difference is if you're running up the stairs, you're exerting work, you're doing work at a faster rate. And the rate at which you're doing work, the rate at which you're using energy, is called your power. So, in regular common parlance, power and energy and work all kind of sound like the same thing. In physics, they have separate specific meanings. Um, Work and energy, they have the same units. They're kind of the same thing. Those are almost interchangeable. But power is the rate at which work is done. So your formula for that, P equals W over T. Power equals work over time. So power is also a scalar, and the unit of power is W for the watt. So 1 watt is equal to 1 joule per second. So this annoys people. There's no way around this. The W in this formula stands for work. The W in this formula stands for watts. There's no way around it. It's just going to be confusing. With practice, you figure it out by context, which thing is which. So the SI unit, System International unit for power is the watt, but we also commonly use HP, horsepower, which is about equal to the rate at which a horse can do work for a sustained amount of time. So 1 horsepower is about 746 watts. So if you do that much work, 16,537.5 joules, by walking up the stairs in 40 seconds, what is your power? And how about if you do the same amount of work by running up the stairs in 20 seconds? So remember your formula for power, P equals W over T. So you plug in the power when you're walking, it's that amount of work divided by the time it takes you to walk up the stairs, you get 413 watts. The power you're exerting when you're running, it's the same amount of work divided by the time it takes you to run up the stairs. It's half the time, so your denominator is half as big, so it takes twice as much power, 826 watts. So how does power relate to velocity? So assume that theta is 0 degrees. Cosine of 0 degrees is 1. So basically what I'm saying is, even though when you run up the stairs, you're kind of zigzagging back and forth, just pretend you're going in a straight line. It makes the math easier. So P equals W over T. W, work, is equal to force times displacement times cosine of theta, but we just determined that theta was 0 degrees and cosine of 0 is 1. So you can just write work is FD. Then you bring out the F, and now you have D over T. And remember, D over T is equal to velocity. So that means this P is also equal to this F times V. Power also equals force times velocity. You can use this formula sometimes. It's not as useful as this one, power equals work over time, but sometimes it's a nice shortcut you can take. So if you apply that much force as you walk up the stairs at this speed, what is your power? How about if you run up the stairs at this speed? So power equals force times velocity. Your power when you're walking is the force you're exerting, 661.5 newtons, times your walking velocity. You get 413 watts. If you're running, it's that same amount of force. Remember, you're applying the same amount of force if you're walking at a constant speed and if you're running at a constant speed. So that same amount of force times your running velocity gives you this number. So these are the same numbers we got before when we did this. We solved for power the other way. You get the same answers. It should work out. The same thing is physically happening in either case. So you should get the same numbers no matter which way you go about calculating it. So what do you buy from the electric company? Do you buy power or do you buy energy? The correct answer is you buy energy. Power is the rate at which you're using energy. It's energy per time. And the electric company doesn't charge you more for using your power very quickly. Or, I'm sorry, for using your energy very quickly. They only charge you for the total amount of energy you use. So part of adulthood is paying electricity bills. If you look at the bill carefully, you'll see they charge you by the kilowatt hour. So kilowatts is 1,000 watts, which means it's 1,000 joules per second. So 1,000 joules per second times this length of time it's an energy per time times the time. It gives you an energy. So it turns out if you do the math, 1 kilowatt hour is equal to 3,600,000 joules. Another way of writing that is to say 3.6 times 10 to the 6 joules. And still another way of writing that is to say that's equal to 3.6 capital M, capital J. Your metric prefixes, capital M means mega, it means a million. So quick discussion of light bulbs. There are basically three kinds of light bulbs you can buy anymore. You can buy an old-fashioned incandescent. We've been using this kind of bulb for more than 100 years. You can buy a CFL, a compact fluorescent lamp. So we used to just, back in the day, fluorescents were only the big long tube kinds of things. Eventually we got good enough in manufacturing them that we were able to turn them into this, curly helixy spiral type shape and put all of the other things you need here. It's called a ballast. Don't worry about it. Fit all of that into such a small package that you could make a regular light bulb that fits into a regular old-fashioned, this is called an Edison socket. There's a name for it. And then finally you have the LEDs. So the LEDs, the light-emitting diodes, these are the best kind. So all three of these bulbs are giving you about the same amount of light as measured in lumens, but they're using very different powers. Incandescent gives you this amount of light using 60 watts. A CFL gives you about the same amount of light. It only uses about a third as much wattage, so it's using its energy one third as quickly. And the LEDs will give you about the same amount of light, but these guys are only using about a sixth as much power as the old-fashioned incandescent. So which should you buy? The incandescents, these are the cheapest to buy, but they're the most expensive to use because they're using their energy much faster. They have higher power, so they're using the energy much faster. So your electricity bill is going to be higher month per month, and per year it'll be this number. The other thing is these guys don't last very long. A typical light bulb will last for about a year, and then you have to replace it. So even though it's cheaper to buy it once, it's more expensive to actually use it, and you're going to have to keep replacing it. So it ends up being more expensive in the long run. I'm going to skip CFLs because these are largely going away and jump to LEDs. So these are going to be the most expensive bulbs. They're not really this much. This graphic's a little bit old. They've come down in price. But they still will be the most expensive kind of bulb. However, they're the most efficient. They use the least amount of energy to give you the same amount of light. They provide the same amount of light using way less power. They're also super, super durable. They last a long time. They're more resistant to being dropped is one thing. They're not made of glass, so that helps. They don't have the very delicate filament inside, and they just last way longer. So even though they're more expensive to buy once, they're cheaper to actually use, and you won't have to replace them nearly as often. So real quickly, when you're buying bulbs, it's confusing how they're packaged if you're buying an LED bulb. So if you look at this guy, look at this little inset right here, there's probably going to be a big number that says it's a 60-watt replacement bulb. So that doesn't actually mean what it seems to mean. This bulb is not a 60-watt bulb. It doesn't use 60 watts of power to provide light. It actually only uses 8.5 watts. So why do they even say this? It's because we, as Americans, and probably everyone else in the world on this one, honestly, for the longest time, we only used the old-fashioned incandescents, and we got used to talking about their light output in terms of the amount of power that they used. Ideally, we would always have been talking about their light output in terms of their lumens, which is their actual light output. But instead, it was easier just to talk about their wattage. So if you pick one of these up at the store, read the box carefully. So this guy, it's not actually using 60 watts of power. It's only using 8.5 watts. What the 60 watts means is that it gives you as much power as the old-fashioned incandescent bulb. So easy bake ovens. These are fun toys. Even people of your generation seem to still know what these things are. Why can you make an easy bake oven using just a regular incandescent bulb? The reason is incandescent bulbs are actually very, very inefficient at their job of producing light. So if you plug the bulb in the socket and turn it on, only about 2% of the energy of the power that it's using, actually ends up being visible light. The rest of it is wasted as heat. So a light bulb is actually very, very good at making heat and pretty poor at making light, at least an old-fashioned incandescent. So that's why you can use one of those to make an easy bake oven. If you have an easy bake oven and the bulb breaks, you just replace it with a regular incandescent bulb, and it'll cook your weird little brownie for you. So don't replace it with an LED, because the LED is not going to use nearly as much power, and it's not going to waste nearly as much power as heat. So way better there. So here's a crash course video if you want to watch it. I think she talks a little fast, so I don't know. Can't honestly recommend this, but it's there. You can watch it if you want. So quick review, check your memory. What is the formula for power? The formula for power, at least our main formula, is P equals W over T. We also have P equals FV, power equals force times velocity, but we don't use that one as much. So what are the units of power? The units of power are watts. W for watts. Again, this gets confusing because in this formula up here, this W is work. Power is work over time. In this little formula down here, this is really the definition of what a watt is. This W doesn't stand for work. This W stands for watt. A watt is a joule per second. It's annoying. It's confusing. I know. I can't help it. Deal with it. So hopefully that helps.